Hello everyone, welcome to our channel. In today's video, we are diving into Interview Ready, Learn DBMS Fundamentals. Your quick guide to learn DBMS concepts and cracking interview questions with confidence. Let's get started. What are the main components of a DBMS? A DBMS comprises several core components that together facilitate data storage, retrieval, and management. Query processor interprets and executes SQL queries submitted by users. Storage manager manages data storage, retrieval from disk, and data structure like indexes. Transaction manager ensures the asset properties, atomicity, consistency, isolation, durability during transactions. Buffer manager manages memory buffers that temporarily store disk blocks. Authorization and integrity manager enforces security constraints and data integrity rules. DDL compiler interprets schema definition commands, e.g., create, alter. DML compiler translates data manipulation commands, e.g., select, insert. What are the different types of languages in DBMS? DBMS languages are categorized into DDL, data definition language, defines database schema. Commands, create, alter, drop. DML, data manipulation language, manages data operations. Commands, select, insert, update, delete. DCL, data control language, controls access to data. Commands, grant, revoke. TCL, transaction control language, manages transactions. Commands, commit, rollback, save point. What is a transaction in DBMS? A transaction is a sequence of operations performed as a single logical unit of work. It must satisfy asset properties. Example, transferring money between two accounts involves debiting one and crediting another. Both must succeed or fail together. Let's understand how a transaction works in a real-world scenario, like transferring 100 rupees from account A to account B. Step 1, start transaction. The database begins a new transaction. This ensures that all steps are treated as a single unit, either all succeed or none at all. Step 2, read balance of account A. We check the current balance of account A, let's say it has 1000 rupees. Step 3, debit 100 rupees from account A. We subtract 100 rupees from account A. This new balance, 900 rupees, is written back to the database. Step 4, read balance of account B. Next, we check the balance of account B, it currently holds 500 rupees. Step 5, credit 100 rupees to account B. We add 100 rupees to account B. The new balance becomes 600 rupees, which is now saved. Step 6, commit transaction. Finally, we commit the transaction. This tells the database to permanently save all the changes made during this operation. The transaction log now confirms, transaction 102 committed successfully. What are the different transaction states in DBMS? In DBMS, a transaction moves through various states during its life cycle. Here's a breakdown of each state along with an example. Active, the transaction is being executed. All operations, reads, writes, happen in this state. Example, a user initiates a money transfer between accounts. Partially committed, all operations are executed, and the transaction is about to be committed. Example, all balance updates are complete and ready to be saved. Committed, changes made by the transaction are permanently saved to the database. Example, the money transfer is completed and reflected in both accounts. Failed, something went wrong during execution, e.g., power failure, crash. Example, server crash before completing the credit operation. Aborted, the system rolls back the transaction. No changes are saved. Example, debit is reversed, and the system discards the transaction. What are the asset properties of a transaction? Asset stands for atomicity, consistency, isolation, and durability. These four properties guarantee that database transactions are processed reliably. 1. Atomicity, all or nothing. A transaction must either be fully completed or not done at all. Example, you transfer 1000 rupees from account A to account B. If debit from A succeeds but credit to B fails, the entire transaction is rolled back. 2. Consistency, preserves valid state. A transaction should bring the database from one valid state to another. Example, if the total balance in the system must be 10,000 rupees, it should remain the same before and after the transaction. No money should appear or disappear due to bugs. 3. Isolation, no interference. Concurrent transactions must not affect each other. Example, if two people try to book the last ticket at the same time, the system ensures that only one succeeds, no overbooking. 4. Durability, once done, always done. Once a transaction is committed, the changes are permanent, even in case of a system crash. Example, if a payment was successful, it remains recorded even after a sudden power outage. What are the integrity rules in DBMS? In DBMS, integrity rules are used to maintain accuracy, reliability, and consistency of data. These rules ensure that only valid data is entered into the database and that relationships between data remain correct. Types of integrity rules in DBMS. 1. Entity integrity rule. Definition. This rule states that every table must have a primary key, and that primary key values cannot be null. Purpose. Ensures that each record, row, is uniquely identifiable. 2. Referential integrity rule. Definition. This rule states that a foreign key in one table must match an existing primary key in another table. Purpose. Ensures relationships between tables remain valid. Why are integrity rules important? First, prevents orphan records, e.g., employees with no valid department. Second, avoids duplicate entries and null values in critical fields. Third, maintains data quality, especially in relational databases. How does a database maintain data integrity during transactions? Data integrity refers to the accuracy, consistency, and reliability of data stored in a database. During transactions, DBMS employs several mechanisms to ensure that the data remains valid and trustworthy, even with concurrent operations or system failures. Atomicity ensures all steps in a transaction complete or none do. Consistency guarantees the database transitions from one valid state to another. Isolation prevents concurrent transactions from interfering with each other. Durability ensures committed changes persist even after system failures. Primary key constraint prevents duplicate or null values in uniquely identifying fields. Foreign key constraint enforces valid links between related tables. Check constraint restricts values based on a condition. Transaction control (TCL) manages transaction completion using commit or rollback. Triggers automatically enforce rules or validations during data operations. What is concurrency control, and why is it important? Concurrency control refers to the techniques used in a database management system, DBMS, to ensure that multiple transactions can execute simultaneously without interfering with each other, while maintaining data consistency and isolation. Why is concurrency control important? Prevents data corruption, ensures that changes made by one transaction do not interfere with others. Maintains data accuracy, guarantees that users see consistent and correct data. Supports multi-user access, allows several users to work with the database concurrently without issues. Preserves asset properties, especially isolation and consistency. Avoids anomalies, like lost updates, dirty reads, and phantom reads. Real-life analogy: imagine two people withdrawing money from the same ATM account at the same time. If both see a balance of 10,000 rupees and withdraw 8,000 rupees simultaneously, without proper control, the account might go negative or be left with incorrect balance. Concurrency control ensures that only one withdrawal is processed for a parent record, the account, at a time, maintaining data consistency and preventing such conflicts. Concurrency control techniques. First, log-based protocols, use of shared, read, and exclusive, write, logs. Second, timestamp-based protocols, assigns timestamps to transactions to determine execution order. Third, optimistic concurrency control, assumes low conflict and checks for issues at commit time. Fourth, multi-version concurrency control, MVCC, uses multiple versions of data rows to allow read, write operations simultaneously. Problems without concurrency control. First, lost update, two transactions overwrite each other's changes. Second, dirty read, one transaction reads data that another hasn't committed yet. Third, non-repeatable read, a transaction reads the same row twice and gets different data. Fourth, phantom read, a transaction re-executes a query and sees new rows inserted by others. What is a deadlock in DBMS, and how can it be avoided? A deadlock in DBMS occurs when two or more transactions are waiting indefinitely for each other to release locks on resources, like rows or tables, causing the system to freeze those transactions permanently. How to avoid or handle deadlocks? First, timeout mechanism. Automatically aborts a transaction if it's waiting too long. Simple and commonly used. Second, resource ordering. Assign a consistent order to resource acquisition. Transactions must request resources in that order to avoid circular waits. Third, wait die scheme. Older transaction waits, younger one is aborted. Fourth, wound wait scheme. Older transaction preempts the younger by forcing it to roll back. Fifth, deadlock detection and recovery. Periodically checks for deadlocks. If detected, rolls back one or more involved transactions. What is optimistic and pessimistic locking in DBMS? 1. Optimistic locking. In this locking strategy, it assumes conflicts are rare. It allows multiple transactions to read data without locking. At commit time, checks if any conflict occurred, i.e., data was modified by another transaction. If conflict is found, then roll back or retry the transaction. Best for read-heavy operations. Ideal in low-contention environments where most transactions don't conflict. 2. Pessimistic locking. In this locking strategy, it assumes conflicts are likely. It locks the data immediately when it is read to prevent others from accessing or modifying it. Other transactions must wait until the lock is released. Best for write-heavy or high-contention environments. Common in financial or banking systems where accuracy is critical. Key differences: optimistic locking, no immediate lock, conflict is checked later. Pessimistic locking, lock is acquired immediately to prevent conflicts. Thanks for watching. I hope you found the video helpful. If you liked it, don't forget to give it a thumbs up and subscribe to the channel for more interview-ready content.